Good morning, class. Today, let me talk a little bit about the project 2. Okay, I posted this description on Moodle. Okay, I hope you already read it, and if you have any question, let me know. Let me explain a little bit. Okay, in project 1, you did a conduction heat transfer problem. Okay, it's 2D. Now, this is project 2. It's a little bit more complicated problem. So this is the 3D fluid mechanics and the heat transfer problem. Okay, so we are trying to simulate a reaction, a tubular reaction. Okay, simulate the reaction in the tubular reactor. This is just portion of a tubular reactor. Okay, so if you go through the tutorial, you know the geometry, right? And the main tube, the bigger tube, okay, it's a bend, right? And then also a small injection port at the turn, right? So the story is this, okay, this is the reactor. We are doing the, polymerization reactions, okay? Although doesn't require you to actually simulate the reaction. We're just simulating the mixing, right, for two different fluid. But this story is like this. It's a tubular reactor. The main flow is ethylene. Okay, polymerization reaction, ethylene become bigger molecules, right? Become polymer. Okay, so in order to initiate the polymerization reaction, okay, we need to inject something called initiator. Okay, in this problem, acetylene is a initiator. Okay, ethylene in the main flow, in the main tube, will mix with the acetylene you injected through the injection port. Okay, so it's the initiator. The better the mixing is between the acetylene and the ethylene, the better the mixing is, the better reaction will happen, right? So the goal is for this project is to see, how well the acetylene mixed with ethylene in the main flow. Okay, that's why in the boundary condition, this is a 3D simulation with flow and with heat transfer. So you also need to specify boundary conditions. In the 2D simulation, like in project 1, the boundary is just a line, right? It's 2D. Now it's 3D simulation. The boundaries are the surfaces, okay? All the surfaces that enclose this volume, these are the boundaries, okay? So all the boundaries, you need to specify boundary conditions. Okay, does that make sense? Okay, boundary condition include the flow boundary condition, which is velocity, as well as the temperature boundary condition. Okay, temperature boundary. So the main flow, the ethylene in the main flow and the acetylene in the injected flow, they have different temperatures. Okay, I think the temperature of the main flow is 300 K. Velocity is 1 meter per second, and the temperature of the injected flow is 400 K, and the speed is 5 meter per second. So the acetylene injection is faster and it's harder. Okay, so that's the story. So then these two fluids will mix in the reactor, and your fluid simulation will tell how well they're mixed. So the other thing I want to talk about is for this fluid simulation problem, it's not just single phase flow. It's just like not just one fluid. You have two fluid, right? So that's why in the tutorial I show you how to specify the multi-phase flow model. You have two different fluids, so you have two different phases. So two phases occupy the entire volume of this reactor, right? So we use something called volume fraction to determine the percentage of volume occupied by each phases. Okay, so on each grid point, the simulation result will give you a volume fraction, which is between 0 to 1. Okay, combine these two fluid, it will be 1, right? So 1 is a fraction of the 100%. Okay, so that's a value we want to look at to show on each surface or on each cell even what's the percentage of ethylene and what is the percentage of acetylene. Okay, that's one of the integrations then we can use to show that how well the mixing is. Okay, so these are the background information. So you are simulating a fluid, okay, with two phases as well as the temperature. Okay, energy equation has to be turned on too. Okay, so I guess this is the background. Then in this project, okay, the tutorial will show you one case, right? This is the one case. The injection port is down there, okay, at the bend. I can tell you that that design of the injection port is not very efficient or not very effective. The mixing is not too good. Okay, if you see the result, you will see the acetylene being pushed to the one side of the tube basically because of the main flow. Okay, so obviously the direction of the injection is not very, how to say, optimal. Okay, so for the purpose of mixing, so I want you to design two different cases. Okay, you can change the injection port everywhere you want. Okay, you can change it. Okay, and you can also change the angle of the injection, but you are not allowed to change the length and the size of the injection, as well as the boundary conditions. So the speed is still 5 meters per second all the way, all for all your cases. The temperature is still 400 degrees all your cases. Okay, the only thing you can change is to change the position of the injection port. Okay, so it's up to you. That's a design project. So if you can, find a better design, that would be great. Okay, so you can have two additional tries in addition to the origin case that you run from the tutorial. Okay, so total 3 cases. I want you basically show the difference in the result of the 3 cases. Okay, I hope your 2 cases are better than the original case. It doesn't have to be all bad. Both of, at least I want you to provide one better case, okay, than the original design. The original design is your benchmark. Well, it's a bad benchmark. It's a worst case. You shouldn't get anything worse than that. Okay, so I want you to see your design. Okay, change the injection port, okay, location and the direction to make the mixing better. Okay, so here are the report requirements. So how to show the result to show that mixing better. Okay, I want you to plot the history of the average temperature and the acetylene volume fraction at the outlet surface. So you have to calculate the average temperature and the average acetylene volume fraction. By the way, I just want you to output acetylene volume fraction because the other side is ethylene. So if it's 0.5, then the ethylene is also 0.5. Volume fraction, right, from 0 to 1. It's a percentage. So you output 1, that should be enough. Okay. So you have to do an average. So when you create a monitor, okay, I think in the tutorial it already show you create a average temperature monitor at the outlet. Okay, for the outlet average temperature as well as the outlet average volume fraction of acetylene. Okay, so the 2 monitor to capture average data at the outlet, right? So that's what I want you to output at the outlet. Okay, so I want you to show and compare between the 3 cases. Okay, and also displays the final temperature and the acetylene volume fraction on the contours, okay, on the central cutting plane. So I think tutorial also show you how to show the result in the center cutting plane of the reactor. Okay, it showed most of the story, by looking at the center cutting plane. Okay, and also show the contours at the outlet surface. Okay, outlet surface, that tells, right? It's eventually at the outlet, see how well they mix. Okay, for those contours, I really want you to set the same color range, the values for all the three cases when you compare. When you compare them, okay, you want an apple-to-apple comparison among the three cases, right? So be sure to set the range of the color. You can actually uncheck the auto range, manually putting the maximum or minimum values. Okay, then the color represent the value. Okay, so among the three cases you compare, the color represents the same values, so you can tell which one is better. Okay, without doing that, the color didn't tell anything, right? If the color representing different values, then it's not good, right? You cannot see the comparison. Okay, very important. Set the contour color range the same for all the three cases. Okay, this is number 3. Okay, so I want you to make one video showing the temperature evolution in the reactor. Okay, the temperature, I think in the tutorial already show you how to make the video. I just wanted to make a temperature video. I don't need you to make a volume fraction video, because it takes longer to reach stable solution for the volume fraction. Temperature is shorter, so save you some time. Just make a temperature video to show me that you are able to do the video. Okay, and the related discussion, very important. You have a lot of results, a lot of physics to discuss. I want you to discuss the physics related to your result. Very important for your report. Okay, that's a big portion of my points, gradings. Okay, on this discussion, and you're not just print out all the results to me without any discussion. Okay, the key is to, when you see the result, you are able to analyze it and tell the story. Okay, so that's very important. Okay, again, this is a design project. It's up to you how to design the injection port. Listen, very important. I don't expect to see any of you get exactly identical result. I don't think with independent work you would design exactly identical cases. Okay, I don't believe that. If I see identical results from 2 of you or 3 of you, I think you basically didn't do the work honestly. Okay, so I don't expect to see any of the same result from any of you. Okay, it's independent work, individual project. Okay, don't do that. Okay, I can easily tell. Okay, submissions. Okay, you need to submit the report, all the case and data, and monitor all the record. Okay, all the results showing on your report, you have to save those records, save those data files. I need to see it. I may be able to run it, right? Also the movie file, it need to be submitted. Again, everything has to be zip into one package to submit. Okay, so this is my simple explanation of the project. I hope that this video answers some of your questions. Okay, I'm pretty sure you have more questions. Feel free to ask. Use any method. Okay, email, or even you can invite me to a Zoom video or whatever. Okay, I'm here to answer your questions. I think this is the good project. It's a design project. Use the software, use the knowledge. This is the state of art. Okay, if you can, being expert on using the software to do helping some design, that's exactly the goal for this particular software. Okay, so you have plenty of time. This is the last project, right? You have plenty of time from now to the end of the semester. So explore the software, learn it, and it's good for you. Okay, it's really good for you, and try to have a good project and going, and learn it, and also have fun, right? Have fun with this. Okay.